Well, this is Mariló Martín Gasulla, and right now, as it says there, in PTV Group in headquarters in Germany. I'm in academia and research as a product manager. And since formerly I was a PhD student at the University of Florida, I'm really excited to see these new PTV talks that we are starting today. So here we are. Brandon?
Thank you, Maril. Hello, my name is Brandon Button. I am the Licensing and Academic Accounts Manager for PTV Group America. If anyone has any questions regarding academic licensing or general academic questions, feel free to reach out to me following today's presentations. With that, I am excited to introduce our first presenter today, Hafiz Usman Ahmed from North Dakota State University. Hafiz, you may begin when ready.
Okay, all good. So can you see my screen?
Yes.
Okay, so thank you, Brendan. So hi guys, today's presentation topic is sensitivity study of driving behavior for autonomous and connected vehicles using microsimulation tool. My name is Hafiz Usman Ahmed. I am currently a graduate research assistant and a master's student at Civil Environmental Engineering, North Dakota State University. A quick introduction about me. I am professionally associated with the field of travel demand modeling and microsimulation modeling, and I do have interest towards autonomous and connected vehicles modeling for. So my advisor is Dr. Ying Huang. She is an associate professor at Civil and Environmental Engineering at North Dakota State University. So let's introduce the topic for what are the benefits that we expect from the vehicle automations and the infrastructure automation. It is expected that the end user benefits we will get in terms of traffic congestions, fuel consumption, and also we will get driver safety, enhanced mobility, and also reduction in the driver's fatigue levels or the stresses. It is expected that the autonomous vehicles, which is AVs, and connected autonomous vehicles, CAVs, are expected to improve traffic flow and safety. And by means of traffic flow, it means that increasing the capacity, reducing the delays, and reducing the number of crashes, conflicts, and like that. So it is expected that the self-driving cars will require several years to completely penetrate the local traffic market. So therefore, it is important to investigate the impacts of the mixed traffic. So by means of mixed traffic, it means that the automatic cars and the conventional cars that is driven by the human drivers. So what is the objective and methodology of the study? First is to conduct a sensitivity study of the car following model, which is the VDMan 99 model, and AV ready options. I will explain it later that what does the AV ready option means for the CAVs and AVs using different market penetration rates. So part of the study is to develop a new mathematical model, actually a car following logic, which we are calling it as a CACFM, which is the cumulative anticipative car following model for automatic cars. And then once the proposed model is developed, we use that model, like the mathematical model and the existing car following logics. W99 here means the VDMan 99 model, and ACC and CACC are famous car following logics that is used by different researchers for modeling the autonomous and the connected vehicles. So ACC is adaptive cruise control, and CACC is just an extension of ACC, which is the cooperative adaptive cruise controls. So we take all these models and we model that in the Vissim APIs. So Vissim API is application programming interfaces, and it includes COM interfaces, driver model DLL, and different things. So as a case study, we have a single lane network, multi-lane network, and then once we develop the network, we estimate the capacity using the effective evaluation configurations that is provided by the Vissim, and as safety is done through the SSAM. SSAM is a safety surrogate assessment model which is developed by the Federal Highway Authority in USA that is used to compute the safety benefits of any network. Connected technologies and ADAS. So ADAS is Advanced Driver Assistance System, and connected technologies we consider V2V communication, V2I communication. Here V2V means vehicle to vehicle communications. So in a case that two vehicles can communicate with each other, they can pass their information like speed, velocity, headway. So it helps in increasing the safety benefits and other things. V2I communication is a vehicle when communicate with infrastructure. So vehicle to infrastructure. A vehicle can communicate with the roadside units like for example, a traffic signal or the sensor that is embedded in the roads. I-to-I communication is infrastructure to infrastructure communications. So two traffic signals can communicate with each other, and they can share the status of traffic lights and other things. So, and what does that ADAS means? It actually supports a driver in terms of performing the different driving tasks, and then in general it provides convenience, efficiency, and improving overall driver experience. As we know that today automobile industry are producing cars that are equipped with several advanced technologies like cruise controls, blind spot detections, lane departure warnings, and others. So a short introduction about the ACC and CACC. Let's consider the ACC. So it talks about the communication of two vehicles. So the follower vehicle can get the speed and headway of the leading vehicle, and what it helps? It helps that the follower vehicle can adjust the speed and safe gap. So concludingly, they can move on a same speed. CACC, which I just explained, that is an extension of ACC. It forms platoons, and what is a platoon is like a stream of car in which one is a leader and other are just the follower. So the leader dictates the information like what speed to move on, what headway you should keep, so like that. And it's done by the V2V communication. Background and the need of research. As we know that car following models are developed to car following models actually defines the behavior of a driver and how it interacts with other vehicles longitudinally. So there are some famous models which you know, that GHR, safety distance, psychophysical, and OVM and IDM. So Vissim uses a psychophysical car following model, which is the VDMan 99 and 74. Summary. So these models are built to replicate the driving behavior of humans, which is good. But in terms of shortcomings in the context of the AVs and the CAVs, these models were originally developed for the human drivers and not for the future automatic cars. So they are not built by means of to conduct the multiple communication or multiple vehicle communication. So in the contrast, the advanced driver assistant car following logics, which is I just defined ACC and CAC and other multiple multi-anticipative car following logics, these are developed to conduct effective V2V communication. So they take the real-time traffic data is recorded by other vehicles, which is the surrounding vehicles, and they use them. But anyhow, they use without filtering for the optimum values. And the control of change of acceleration is based on the actual values without considering the desired values. Important in case of unusual condition. What does that mean? It will be explained in the next slide, that why it is important to consider both the actual values and desired values, and then decide which one is more optimal for the current situation. So what is the proposed CA-CFM car following logic? Key facts are, again, it uses a real-time traffic data for the multiple vehicles, but using the V2I system, which is vehicle to infrastructure system. And for example, it takes the data from the sensor that is embedded on the roadways. And then the model is an extended form of CACC car following logics, which considers the multi-anticipative car following techniques. Here, the target car, I mean that the car that is equipped with the CACFM car following logic, it uses the optimal data from all other conventional vehicles. Now, this point is important. As you see, the ACC and CACC, it is important that all the vehicles that is using the CACC technology should have that equipment or should have that following logic built in that. But in our model, we are not saying that the other cars, which is the conventional vehicles, should have this CACFM car following logic should be built in, because we are getting the data from the V2Y system and not from the V2V system. So it doesn't matter whether it's a conventional vehicle or it's an automatic car. And then interaction is developed with every two vehicle pair, and the target car evaluates the desired and actual values, which is acceleration and velocity of all other vehicles, and takes a safe decision. So let's consider there is a traffic stream of 10 cars. So the vehicle in the downstream gets an incident. So the following vehicle needs to communicate with all the vehicles, because then you can decide that what is safer. And then it is important to consider what is the desired values and what is the actual values. In case of unusual conditions, it is safer to use the desired values, not the actual values, and then the car decides whether how to keep the safe distance or change a lane and etc. Why choose PTV Vism? I'm already more than 8 minutes, so I just quickly go through these things. PTV Vism provides different options like external driver model, developing through APIs, calibration of existing car following model parameters, effective evaluation techniques. As I told you, it has different options that you can use to evaluate the capacity and safety. Built-in features for AVs, which is one of the greatest tool that is provided by the Vissim. So you don't need to do so much coding and so much scripting. Already they have provided some options. Robustness of the graphic user interface. We know that 3D modeling is one of the great option. A strong technical support by the PTV group and LinkedIn Vissim forum. LinkedIn Vissim forum is one of my favorite option. Whenever I'm stuck somewhere in the research, I just throw a question on the LinkedIn Vissim forum, and that's really helpful. And similarly, the technical support. So we know that there are what is the AV ready tools. So with the latest release of Vissim 2020, and I think even in Vissim 11, they have provided options that is AV ready, which is autonomous vehicles ready, because of the coexist project and the Vissim. There are several options available that a user can use to model the autonomous vehicles. One of the important option is platooning possible. So now the user don't need to do any external scripting or any coding, and then they can use this tool. And then there are some car following logics already available in the software, which is AV cautious, normal, and aggressive. Now quickly go through, because of this research we are doing so many experiments like single lane, multi-lane. In this presentation, because of the shorter time, I'm just considering the single lane freeway 5-kilometer network. We use the different models ACC, CACC, CSFM, and we model that in the DLL files. And then in order to analyze the critical safety assessment, we introduce a slow moving vehicle that stops in a midway of the traffic network, and then it creates a hypothetical incident or a shock wave, which is important to understand, like what are the benefits of in terms of safety for different models like ACC, CACC, and CSFM. So this model is just developed using this simple stop sign in the Vissim network objects. So we did multiple simulation runs with different random seeds and different sets of speeds and volumes, and then we develop a 15 minutes interval to evaluate the travel time, delays, and queues. So Vissim do generates a vehicle trajectory file, which is the TRJ file, from each successive simulation run. Then that file is used in an SSAM tool, which gives us the number of conflicts that occurs. So I'm just showing you the results that we got using the, if you see on the left hand side, there is the default W99, which is the VDMN99 default car following model in the Vissim, and ACC, CACC, and CSFM. And you can see that the number of conflicts were reduced in using the CACFM. Actually, the CACC and CACFM are actually performing more closer. But anyhow, the in terms of safety, the CACFM leads from other following models. And then this another table is just for the another set of the vehicle, like volume is 2200 vehicles per hour per lane for the 60 miles per hour. The first one was 45 miles per hour, and even in this 60 miles per hour, we can see that the safety benefits are more than the other models. And because it's a single lane network, we are just considering the rear end conflicts only. And as I told, that the robustness of the graphic user interface of the Vissim software, this is just an explanation of the real values that we took in a snapshot from a network. So that this green vehicle is a vehicle that stops in a midway, and it creates an accident. And the red car is the one that is controlled not by the default model, which is the VDMN, but with the external driver model that we develop. It can be an ACC or CACC or CSFM. So in the last, I will just quickly go through this simulation runs. I'm already out of time. So you can see that there are 4 links, and each link is using a different driving logic. So default VDMN99, ACC, CACC, and our proposed logic CACFM. And then in this, you can see this red line is a vehicle breakdown spot. Here, the green car stops and it creates an incident in a way. And then this red vehicle is a vehicle that is equipped with the external driver models, and the black cars are just using the default model. So this combination gives us some insights of what is happening and how which model works better. So with that, I'm going to ask if you have any questions. So feel free to ask.
Thank you, Hafiz. We do have a couple questions. To what extent the AVs will be practicing useful in congested traffic?
Okay, so it depends like what kind of scenario you are modeling this AVs. So whether it's so we are considering a freeway network. I know that once it goes to the urban network, it's going to be more complicated. So in terms of freeway, it is surely going to increase the capacity. So normally we know that the highway capacity manuals give a capacity of 2200 vehicles per hour per lane. We have seen a literature review that it can increase a capacity of more than 3000 or 3200 vehicles per hour per lane. So yeah, it's going to improve the overall efficiency of the network. Yeah.
Thank you. We have another question. Would be great if you can further explain platooning concept in Vissim.
Okay. Okay, that's good. And by me, I mean to say that platoons already those people who are using Vissim 2020, this option is already available in the software, and PTV Vissim have a very good webinar on the platooning. Anyhow, so platooning is like a set of vehicles in which there is a leader. The leader is actually a dictator that dictates what the following vehicles should do. So the following vehicles gives a control to the leader, and the leader can control the velocity, speed, and headway, and the vehicles can follow each other with the closer gaps. So yeah.
Awesome. And then we'll take one more question and then save the rest for afterwards. Did you test a model with significant amount of commercial trucks? We have routes in our state where they're up to 15% traffic. Or how will this model behavior under such conditions?
Okay, this is a good question. For now, we are just considering the private vehicles and the cars only. No trucks is included. Yeah.
Okay. With that, I'm going to pass it over to Murillo, who will introduce our second presenter. If you have any questions about this presentation, please leave them in the chat and we can get to them afterwards. All right, Murillo.
Okay, thank you very much. So now we go to Federico Caprile from Pontificia Univesidad Católica Argentina to present his study on implementation of a Superblock in downtown Buenos Aires. So there we go, Federico.
Yes, I need to have the permission to share the screen. There we go.
Perfect. Thank you.
Is it sharing? Can we see the first slide?
Yes. Yep.
Okay, great. Okay, thank you, Marilo. Hello to everyone. As Marilo just introduced you, I will be presenting my research about the implementation of a Superblock in downtown Buenos Aires. First, I would like to introduce you to our research group about the Transport Research Center, where we do investigations on several subjects as road safety, innovative intersections, infrastructure, and mobility studies. And this work was done during last year with Ingeniero Raúl González and Agustín Poblet. And as to start, we found the need in the Centra to resolve this problem, the city of cars, which I'm sure it can be found in many cities around the world, where during the last century, really the number of vehicles has increased to such degree, to such extent, that they have become a true protagonist of cities, displacing its inhabitants from their own public space. So, as to make way to motorized vehicles, modifications were implemented in cities which slowly generated the degradation of public space. This generated negative impacts in the city, generating traffic jams. And nowadays, we can see this problem, this situation in downtown Buenos Aires, with traffic jams, deteriorated public space, narrow sidewalks, where pedestrians bump into each other. So after doing some research and learning about the postcard city theory, we thought about implementing a Superblock could help us in many ways to resolve this issue. So for those who are not familiar to this urban implementation, a superblock is a group of adjacent blocks which aim to generate an urban microclimate, and by restoring the urban spaces that are nowadays degraded, and it sums a better safety for pedestrians and drivers also. We have two types of streets in a superblock. We have the inner streets, which are these gray ones, which are darker ones, which are pedestrian priority. So drivers can enter into the superblock only with a special permit, and if they do, they should circulate around 10 kilometers per hour, which is 6 miles per hour. And then we have the perimeter streets, which are these wider, light gray ones, which they just enclose the superblock, forming the boundary. So we decided for the design of our superblock, we based ourselves on an existing one, which is located in downtown, which is this one, and we decided to implement a superblock in this area around here. And you can see in the picture on the right how the superblock looks nowadays. We have the leveling of the road with sidewalk, the rainwater channels installed, the bollards, trees. It looks like a good place for pedestrians to walk. So our objective in this work was to study the consequences caused by the implementation of this superblock in this specific area, looking or aiming always to improve and the traffic in the area and empowering the pedestrian. And we are going to do this study by doing a comparative one, comparing the actual situation with two types of superblocks. We have the traditional superblock, which is, as I explained on the slide before, and the second one is a land use superblock, which is designed to help amend the diverse land use found in the district by adapting its streets to its land use mixture and presenting less restrictions. We wanted to know if the second alternative would yield similar results when compared to the first one, and this comparative study was done taking in consideration three areas: traffic, environment, and road safety. So for you to have an idea of how was that we modeled these superblocks in PTV Vissim. This network was comprised by 60 intersections, which meant a really big challenge to us. All intersections included traffic lights, and all vehicles which interacted in a network were adjusted to standard measurements. This meant that we first did a car composition to know how many taxis, trucks, pickups, and public buses circulated around that area nowadays, and we adjusted their measurements to typical makes and models of cars of the Argentine car fleet for us to be representative to the cars of our city. And also different parameters were changed to represent in the best way the city drivers' behavior, taking in consideration the Weidemann 74 theory, because it's not the same a driver from the States than from Germany, than from the Americas or Asia. So we changed those parameters in order to represent in best way the city's driver behavior. And also we needed to include 25 bus lines and 14 bus stops. And in order to do our evaluation, we decided to include 13 nodes in order to have our indicators. These are the indicators that we used in our comparative study. The ones from the left, which are the ones from traffic and environment, were given by the PTV Vissim program software, and the road safety ones were taken from a surrogate safety assessment model. And for here you can see Here you can see the actual situation, narrow sidewalks with a lot of pedestrians, buses really passing by. Those pedestrians are not really a happy place to walk and to pass by. On the right side, you can see the simulation we did on the PTV Vissim. And next, we can see the simulation we did on the traditional Superblock. Drivers can enter here only with a permit, with a specific permit. The maximum speed was 10 kilometers per hour. The traffic lights on the internal intersections were removed because of the low speed the cars were traveling and the low vehicles flows, the low traffic flows we had. It wasn't necessary to include a traffic lights. Some streetways needed to be changed really to improve the circulation inside the Superblock. And of course, public transport needed to be reorganized in order not to pass by through the Superblock. It needed to surround, in all cases, the Superblock, not to enter. And then we did a simulation on the land use Superblock, which was the second alternative. The main change here is that we did an adaptation to land use. We found different land uses in this area, streets that had mainly offices, streets that were mainly commercial and residential. Streets that were offices were implemented by including a pedestrian priority streets. Commercial streets were changed to pedestrian only streets, meaning no cars. And residential areas were pedestrian priority streets as well. And here we decided to have a free entrance for cars in order to eliminate that rigid perimeter the traditional Superblocks generate. But even though we decided to still maintain the maximum speed to 10 kilometers per hour, but we needed to insert traffic lights, as you can see in the intersection, in order to organize the traffic flows. And of course, the reorganization of public transport was done in order not to go through or go inside the Superblock. So as to have a summary of the indicators that we've got here, we have a summary table for you to have a quick glance. After doing 10 simulations with 10 different seats each, let's say 30 simulations in total, we did an average on each indicator. And here we can see the internal nodes, the perimetral nodes, and the external nodes. And in this case, we have the traditional Superblock, and in this lower row we have the land use Superblock, and we can see clearly that the traditional Superblock generates improvements in the insides but worsening in the perimeter, while the land use Superblock doesn't present really a pattern. So as a final conclusion, we had the traditional Superblock with a rigid structure and the land use one, which have a permeable structure. After doing some evaluations with the indicators and doing some data analysis, we decided that the traditional Superblock would be the best implementation for that area. And once we chose the traditional Superblock to implement in the area, we needed to do a traffic flow reduction study in order to know how can this Superblock, accompanied by public policies that aim to discourage the use of motorized vehicles, how can they reduce it? So after doing some study on the net level of service of the area in general, we can conclude that the traditional Superblock can reduce traffic flows in that area in order of 12 or 13% of reduction. So thank you very much for your attention. You can have my email if you wish to contact me, and now we're open to questions.
Thank you very much.
Thank you, Federico. All right, so we have a couple questions.
Okay.
In regards to, oh, it's scrolling away from me. 1 sec. All right, here we go. In regards to the Superblock, apart from the 10 km/h speed limit that will be imposed on vehicles permitted to enter, what about zero tailpipe emissions to encourage a much more livable space for all in the area?
Sorry, zero type emissions? I'm sorry, I didn't.
Yeah, zero tailpipe emissions to encourage a much more livable space in the area.
Yes, of course, that would be a very good implementation that could be included in our study.
Another question we have is, what are the traffic light timings like in the Superblock, and what do you propose to improve it to make it safer and better for pedestrians?
Yes, the cycles that were included inside the Superblock maintained the previous cycles, taking in consideration that we didn't want it to interfere with that. Traffic lights where we went improving the simulation when we could get better results, and those adjustments were made to have the best results possible. I think that traffic light cycles, in those cases, taking in consideration that cars and vehicles need to circulate at a very low speed, they do not need to be very short, but long as to let cars pass by through.
All right. Another question. Is there a reason why your simulation does not show pedestrians traversing the intersection? Pedestrians have a significant impact on traffic flow, thus affecting the levels of service.
Yes, of course. We had the desire of implementing pedestrians on the simulation, but it really was a very big area to encounter. And also we had certain limitations with the licensing. We couldn't include so much pedestrians on our license, so we decided to, in order not to give vague results, to leave them apart and only study the traffic interactions.
All right, and the final question. To prevent such congestion and worsening air quality, several governments are now going to implement the road diet, thus supporting the bicycle lane. Is that possible?
Yes, that is possible. Actually, the city also has a big amount of bicycle lanes inside the Superblocks, and actually on that zone in specific, there was some bicycle lanes that we decided to include there. But once again, adding bicycles to our study was going to be even more challenging. So in order not to have bug results, we decided to leave it apart. But yes, bicycles, taking in consideration COVID and how the bicycle nowadays is expanding more and more, it would be great to include it into the study.
All right, thank you, Federico. All right, I'm excited to introduce our final presenter today, Fernando Cordero from Auburn University. One second, let me make him presenter. All right, Fernando, take it away.
Oh, thank you. Thank you, Brandon. Okay, so the title of this research is comparing a Vissim-based simulation tool and a regression model to forecast intersection crash rates in Alabama. My name is Fernando. I'm a PhD student at Auburn University. Okay. So first, I want to briefly discuss the issue of motor vehicle fatalities in the US. And just to picture this problem, just in 2019, between 36,000 and 38,000 people died in motor vehicle crashes in the nation roads. as a consequence of the increased number of fatalities, there have been different efforts throughout the decades to tackle this problem. And as you can see in the slide, I'm showing just some of the policies that has been passed in some programs. And as a result of these programs and these policies, there has been an improvement in traffic safety. And mainly this has been because of effective planning strategies. And some of these planning strategies are part of the short-term and long-term planning process. At the different levels, we're talking about local cities, metropolitan cities, and statewide planning process. And safety studies has been key in these strategies in the planning. And one tool that has been widely used is crash prediction models. These models help us to identify high crash prone traffic sites. So engineers and policymakers can take the appropriate decisions on which safety countermeasure to implement in order to reduce fatalities. So traditionally, crash prediction model has been based on statistical analysis. And we're talking mainly of two models, the Poisson distribution and the negative binomial distribution. This is just the mathematical representation of the models. They are basically similar. The difference is that the negative binomial includes a dispersed parameter right here that account for over-dispersion in the data. Over-dispersion is one of the constraints of the traditional Poisson distribution model. On the other hand, we have traffic conflict and surrogate safety measure model. These models are not based on crash. They are based on different safety measures, for example, time to collision. So using an analysis of vehicle conflict, we can identify, and using the different measures, we can identify the likelihood of a conflict to occur at one specific traffic site. So for this project, we use PTV Vissim to generate the vehicle trajectories, and then we implement the SSAM tool to do the analysis of the vehicle trajectories. And as I mentioned, this is based on the different surrogate safety measures. So as I mentioned, this project was conducted for Alabama. So we had 18 intersections in two cities. On the left, we have the city of Montgomery, Alabama, and right here we have the city of Auburn, Alabama. And we use a classification to on the intersection. So we use complex and simple categories, and this corresponds to the volumes of traffic and how big the intersection is in terms of the geometry. Not surprising, we observe that in Montgomery, most of the intersections are complex. Montgomery is a bigger city, has more traffic volumes. And on the other hand, Auburn is a college town, less population compared to Montgomery, so most of the intersections were simple. The rest of the data include different intersection characteristics, number of lanes, lane width, speed limit, number of driveways, number of traffic signs, and so on. So we have around 18 different characteristics that we were trying to that we use to identify a statistical relationship between these contributing factors in the occurrence of crashes. Then we had traffic counts. We collect data in the city of Montgomery, and we use historical data from the city of Auburn. We already have data from Auburn. And finally, we use historical crash data for the state of Alabama. This data comes from the critical analysis reporting environment. This is a database specifically for the state of Alabama that collect crash data from law enforcement and first responders. So this is a really good database for safety analysis. And as you can see, this is just a graphic of the average annual crashes. So with that information, we did the microsimulation using Vissim. We run the simulation individually for each intersection. Even though we could have done a corridor study, we decide to do it individually. And in this example, we include as needed. We include priority rule, reduce speed area, conflict areas. The second input include the vehicle volumes, traffic volumes. So we already have, as I mentioned, data for Auburn, and we had to collect data for Montgomery. So we had the peak hour volumes, and we knew the volume for each of the movement. So we just input that as a static vehicle road decision. And finally, we have to create the signal timing. All of the 18 intersections are signalized. However, and I want to highlight this, we have some issues to collect specific and detailed data of all of the intersections. So we have to do a more general analysis. So as you can see, we use like general cycle times. The signal group were very basic. Some of the intersections are actually actuated, but we did not consider them as actuated. And this is something that is really important to mention, because this is going to have an impact in the final result. But we did what, we used the data we had available. And so with that information, we run the simulations. We did 1.5 hours of simulation. And since we are only interested in the trajectory file, that was the only output that we care about. And for validation of the simulation, we use vehicle queue length. So when we did the traffic count, we also took the information on the queue length, how many vehicles were in the queue. So we use that information as possible just to validate the simulation. Again, unfortunately, we did not have vehicle queue length for all of the intersections. What we have right here is the results of the SSAM tool. We have the trajectory files from Vissim, and we input that in the SSAM tool. The SSAM tool runs a statistical analysis of the different surrogate safety measures, and it estimates the number of conflict. As you can see in this table, SSAM gives information on 3 different conflict types, but we were not looking at specific type of crashes. We were looking at the total crashes of the intersection, so we just look at the total number of conflict. Now, also we have 2 equations right here. These equations correlate the number of conflict at the intersection with the annual number of crashes. So we can use these 2 equations with the number of conflict to estimate the crashes. We also run the regression analysis. As I mentioned, we use the negative binomial just because this regression model has a better performance because it accounts for over dispersion in the data. And we have around 18 different characteristics. So we did different models. Within the regression analysis, we did different models. That means that each model had a different set of variables. And we compare these results for each of the models in terms of log likelihood, in terms of the Bayesian information criterion. So we have some parameters to compare this model, and therefore we could choose the best one. And this model right here is the one that had the best performance. As you can see, we found 3 of the characteristics that are significant to the model: speed limit in the intersection, number of right turn lanes in the minor approach, and also the number of lanes in the minor approach. Again, with these coefficients, we can estimate the number of crashes at the intersection. So that's what we did. And this figure right here compares the result from the different models. We're talking about the 2 equations from the Vissim and SSAM model and the regression analysis. And we compare that with the observed number of crashes that we have from CARE dataset. As you can see, this portion of the intersections, they have a really good performance. And on the other hand, this portion had they over predict the number of crashes. And that's not a coincidence because many factors were involved in these results. First of all, this corresponds to most of the complex intersections. So these were more difficult intersections to simulate in terms of the number of vehicle volumes, the signal timing. And this corresponds to simple intersection. They were more urban, less traffic. But even though we can see that the SSAM and the Vissim approach, actually those are really good work in estimating crashes at some of the intersections. So the conclusions of our work are more like a recommendation for traffic engineers in the state of Alabama, because we want to provide them with insight on which approach to take when they have different situations. For example, if they have access to detailed information of the intersection, and we're talking about volumes, signal time. So in that case, Vissim is the best way to go. Also, if they want to look at the performance of the intersection after implementing a specific safety countermeasure. Also, when there's no access to historical crash data, which is a common problem for traffic engineers and transportation agencies. So in that case, Vissim is also a good approach. And we did not apply this, but Vissim is a best approach when you have a Cordero studies, because you can include the behavior of previous and of the intersections in the corridor. And finally, the regression model is really useful when you want to do a quick analysis of individual site. So with that, I would like to acknowledge Dr. Jeffrey Lamondia. He's my academic advisor at Auburn University, Dr. Roche, who provide us with the traffic count for the city of Auburn, and the research team, Mitch, Jacob, Alex, and Nacha. They help us also with collecting the traffic count data. So with that, I would like to move on to the questions.
Thank you, Fernando, for your presentation. We do have a couple questions. The first one is, did you consider a warm-up period for your simulation?
Yes, so we did 1.5 hour of simulation. We did 1.5 hour of simulation. So the first 30 minutes of the simulation were used as a warm-up period.
Thank you. The next question, did you consider negative binomial zero inflated models? Also, was the analysis in SSAM done for the whole network or just for some areas within the intersection buffer zone?
Yeah, so we did not include the inflate zero negative binomial. We use just the gamma distribution negative binomial. And we did not include like corridor. The analysis, we just analyze individual intersections.
Thank you. And then another question, what is the difference between major and minor approaches? I'm afraid I didn't understand this part.
Yeah, so since we are looking at the intersection as a whole, you're gonna have a major road that is gonna be the one with higher volumes of traffic, and the minor road is gonna be the one usually with less volume compared to the major. So it's just based usually in traffic volumes, or is based on how many lanes there are in each of the approach. Let's say southbound, northbound approach against the east-westbound approach.
Thank you. And our final question, what recommendations or improvements would you make or suggest from the results your model generates?
Great question. So some of the recommendations is that Vissim and SSAM is showed to be a very accurate model, but you need to include as many detailed information as possible. So that's one of the recommendations, that if you want to run this type of approach, make sure that you're gonna have as much detailed information as possible. Also, there are gonna be specific situations. If you want to, for example, focus on safety countermeasure, the implementation of a safety countermeasure, then you can take a Vissim-based model approach instead of a regression, for example. So basically, it depends on the situation, on the scenario, the information that you have. That's gonna dictate which of the model better fit to your project.
All right, thank you. With that, we conclude our Q&A session. I want to thank the presenters personally. This was really cool and informative.